Hello and welcome to the lecture on decision trees. So today we're going to be talking about decision trees. This is taking some of the concepts from utility theory and applying them into a multi-stage process so that we can better try and understand how we could evaluate some decisions that we may be facing. So let's start off and look at what a decision tree actually looks like. So here's an example of a decision tree. Okay, and there's a lot of numbers on there, and I'm going to go through them again in a minute, but I just wanted to give you a flavour. So this particular one, it's like trade ticket, keep ticket, and then there's some win and loses in there, the probabilistic events, and there's some values kicking off all around there, and we're going to go through them all in a second. So, one way that you might want to choose an option is deciding on which option gives you the highest expected value. Okay, so given the decision that you make, what does that decision result in, and therefore does it result in the largest expected value? And this is what decision trees are all about. They're about saying, okay, well, if I choose this, then that means this might happen, then I might have to make this decision, and then this might happen, I might do this decision. Okay, and decision trees map that all out, and then we work backwards. So we work from the end, and we work backwards to work out which is the best choice in the end. Okay, so we start from the right, and we move to the left. Okay, so let's start off with an example. Okay, so let's imagine you have a lottery ticket. And that lottery ticket, there's a 45% chance you might win $10, and there's a 55% chance you might win $0. Now, I'm going to offer you a deal. The deal is, you give me your ticket plus $1, and I'll give you a new ticket. And there's a 20% chance you're going to win $25, so more than $10, but an 80% chance you're going to win $0. Do you take the smaller chance of winning money? So what should you do in the circumstances? Well, there's multiple things we need to take into account here. Not only do we need to take account of the chances, but we also need to take into account the fact that you gave me an extra $1. Okay, so that needs to be weighed into the equation. So let's have a look at that decision tree again. So the way the decision tree is broken down is the actual amount you finally get for an option. So you go from the decisions and then there's chances, etc., as shown on the right-hand side. So let's consider this particular option here, which is if you trade the ticket, you're going to get $25, but then you spent $1. So up here in the top right is $24. That's if you win. Now, if you lose, you're going to get minus $1. Okay. Now, if you kept your own ticket, you don't have to pay anything, so you're going to get the $10 or the $0. So let's break down some of the different parts of this. So we got these different types of nodes here. This is a chance node. Brown nodes are chance nodes. And square nodes are decision nodes. So this is where you need to make a decision. Okay. All right. On top of that, what we've got is there's other things here, which is the probability on the chance nodes. So there's a 20% probability on this chance node, and then there's an 80% probability on losing on this chance node. So 80 plus 20 equals 100. So you get 100%. So all chance nodes should all the different options should add up to 100. Okay. Now what we can do from this is we can actually work out the probability, the actual expected value using these probabilities from this set of chance arcs. So now let's look at the actual what the expected outcome is, the expected value of this particular chance node. So it's 0.2 times 24. Or plus 0.8 times minus 1, which is equal to 4. You can do the math on that yourself and just check that out. So that's the case. Okay, so let's have a look at the other one down here. So we always work backwards here. So there's the 0.45 chance to get it 10 and 0.55 chance to get 0. The expected value here is 0.45. So we've got these two options here. So if we go this way, we're going to end up with 4. If we go this way, we're going to end up with 4.5. So what this concludes here is that we should keep the ticket. Okay, the ticket seems like a smart thing to do. So we're going to keep that ticket, and we're going to get a chance of getting expected value of 4.5. So I'm just going to show you the math here a little bit more closely, just so that you can follow correctly, just in case you missed that from the previous slide. So the keep ticket one again was the 0.45 times the 10 plus the 0.5 times the 0, which equals $4.5. Okay, all right, and then the other one was the 0.2 times 24 plus 0.8 times minus 1, which equals $4. Okay, now we can actually collapse the tree down. So instead of actually now having that chance nodes here and here, we just remove them. We make a smaller decision tree, which is, if I go this way, trade ticket, I'm going to get 4. If we go this way, to keep the ticket, I'm going to get 4.5. So again, I'll choose the 4.5. So the trees that you just saw were created using the software here, which you can freely download if you wish. I tend to just do my trees in PowerPoint, but that's just me. But there are advantages from using a software package like Occam's tree. So there's a lot of other decisions that you might actually want to make. So the more classic ones that you tend to see in systems engineering are like choosing between design alternatives, considering the benefits of each and then the probability of the success, etc., coming in there. Hiring contractors, evaluating proposals for a request for funding proposals that might come out from an agency. So this is how they actually may then evaluate the different proposals. So what would happen there? It's like, well, someone's proposed this piece of research. What chance of success do we think they have? And what benefit do we think if they actually are successful compared to not being successful? Okay. So we talk about this probabilistic aspect in decision trees, but don't think of this as just being about chances or gambling, etc. Sometimes in the real world, you know there's potential outcomes on there, and you give a probability to them, and it doesn't mean that you're necessarily gambling. So, for example, you may go for a job interview and say, I've got about 20% chance of getting that job interview. It's an estimate that you've come up with. Okay, it doesn't mean that you're gambling on a job interview. It just means that you're estimating the likelihood of success of that job interview. Okay. Right, so we're going to go for a larger example now. The example here when they've got Texaco versus Penzola. There was a court case. Texaco offered Penzola $2 million. Penzola has to choose between accepting this or making a counteroffer of $5 million. Assume that Texaco can make more than one counteroffer. So we're going to construct a much more complicated decision tree from this now. So here's a decision tree. So here is the decision. So this is Penzola's decision. Do they accept the $2 billion or do they counteroffer with $5 billion? Given that, now Texaco can do some other counteroffers. They can accept the $5 billion, in which case everything's resolved. They can refuse. Then you've got the court decisions, and then they can counter. Texaco can counter with say $3 billion, and then coming back to another decision. No, this time it's going to be Penzola. It's going to choose to refuse that, and they go to court, or they could accept the $3 billion. Okay. Now we've got all the different values that are worked out here from the different aspects and the potential outcomes. Okay, so we've got this other assumption coming in here, which is the High Court decision, which means that actually Penzola is going to get $10.3 million. Mid-court decision will be $5 million, and low court decision will be 0. So this is actually not the types of courts. It's actually the assuming that what are the outcomes from the court case. Okay, and there's a 0.2 chance, a 20% chance that they're going to get the $10 million this way. There's also a 0.3 chance or 20% chance that they're going to get nothing. The court's going to go in favour of Texaco. Okay, so this is the game tree here. So you've got this here. We also repeat this here because if they refuse, if Texaco refuses, if Penzola refuses Texaco's counteroffer, then it's going to go to court, and this is the potential outcomes here. All right, so let's do some breakdowns here. So let's just see if we can, what can we work out here? Well, we've got this probabilistic setup here. We can do these. We can work out these values to the expected values here, and we work it out to be 4.56. And because this is exactly the same here, it's 4.56 as well. Okay. So one crucial thing I want to bear in mind is this is because we've got two different decision makers in here. Now, Penzola wants to get the highest value, which is one of the decision makers. Okay. And Texaco wants to actually get the lowest value possible. Okay. Now, we could include another decision node in here, which we could put here, but this is actually a chance node, if you notice here. So we're saying, we're just going to assume that the way Texaco acts as a probabilistic event, but we could make this into what we call a game tree, and then we could have two decision makers. So we're just going to assume in this case that Texaco's decisions are, 70% chance they're going to accept it. We're going to assume, 50% chance they're going to refuse the counter offer and get caught, and 33% chance they're going to counter with 3 billion. Okay. So we're just going to assume what Texaco does as a probabilistic event here, just to simplify this a bit. Okay, so now we've got down here. So notice we've got this two decisions. We've got decision here and decision here. So what are we going to do in this case? Okay, so what we're going to do here and deal with this. Well, the way we deal with this is we just eliminate the inferior branch. Now, if they refuse the 3 billion counter offer, they've got a expected value of getting 4.56. I'm just using normal expected values here, as opposed to anything like risk averse, etc. You could introduce that and put utility functions as opposed to expected monetary value functions up here. So this means, so what does that mean? Well, that means that, to be honest, in this case, it's like Penzola just might as well refuse this counter offer and get a call because they're going to get more than accepting the 3 billion. So we can eliminate this branch. This is this sort of like backward induction piece. So now the game tree looks a bit like this. So we've eliminated the probabilities for the court case and just made them into an expected value. We've got this expected value here. And now we've got these values here. Now we've got this new game tree that we can play with. Okay, well, let's work out the expected value for this. So we've got this expected value here, 4.63. Okay, so we could go, okay, let's do this one then. Okay, let's see what goes on here. So we're going to, again, crash this down so we can eliminate that, and then we can just see what we're comparing this one to this one. So we see that here, we've got the counter offer with 5 billion, we're expecting to get 4.6 billion. If we accept the 2 billion, then we get 2. So in this particular case, it seems more sensible for Penzola to counter offer with 5 billion and see what the outcome is from that. Okay, because it's more, the 4.63 is more than the 2. So what actually happened? They actually ended up in an agreement where they agreed to pay Penzola 3 billion, which is interesting because from our breakdown that doesn't seem like the actual smartest thing to do. However, bear in mind that we are estimating those probabilities. Maybe Penzola had different probabilities that they chose to use. Maybe they were risk averse. Maybe this seemed the more sensible aspect for them to go. All right.